question 9.3. Prove that TK bisects AKB, angle AKB. So let's go ahead and find where exactly AKB is. So AKB. So essentially what we need to do is what's required to prove is that K2 is equals to K3. So what we require to prove, RTP required to prove K2 is equals to K3. That is our goal here. And remember, K3 is X and C as well is X. So essentially we need to somehow figure out how exactly K2 is also X. So firstly, we know that K3 is equal to C from our previous question, and that was X. So just might use that here. So K3 is equals to C, which is equals to X. Just keep writing it because if we use it just to ensure proven above. And what we can then state after we have that is that K3, and if we look at where K3 is K3 is equals to B2. And the reason for that is where our tan chord theorem is. So therefore, because K3 is equals to B2 will equals to C, so therefore B2 is also equals to K3. So yeah, let's just go ahead and write that down. So firstly, B2 is equals to C, which is equals to, okay, this first tan chord theorem, and therefore, well, B2 is equals to K3, right? Because they are equal to each other. And once we have that, we can then state that in this instance here, K3 would also equals to K2. And for that reason here, if we just make this X, K2 is equals to B2, and that is angles in the same segment. So if we just have a look at, if we use chord AT goes to B2, and because remember we already proved AKBT is a cyclic chord, so now we can use that to our advantage. So there's your angle there at the circumference, and here is your angle K2 at the circumference of this cyclic chord that we proved. So therefore what we can state here is that B2 is equals to K2. B2 is equals to K2, angles in the same segment, and therefore K2 is equal to K3, and because they are equal, that means that TK bisects, which means cut exactly in half, bisects angle AKB.